Alright, let's go. Number 10. The Perytons. In 1998, the Precursor radio telescope in New South Wales began picking up brief, powerful radio flashes that looked identical to fast radio bursts, genuine cosmic signals from unknown sources billions of light years away. Astronomers got excited, then confused, then, for 17 years, quietly desperate. The standard model said these bursts should behave like every other fast radio burst, appear once, come from deep space, never repeat on a predictable local schedule. If the signal was cosmic, its arrival should have nothing to do with anything happening on Earth, let alone inside the observatory building itself. Then someone noticed the timing. The bursts clustered suspiciously around lunchtime. Emily Petroff and her team at the Precursor Observatory tracked down the source in a 2015 paper published in monthly notices of the Royal Astronomical Society. The astrophysical signals, the Perytons, were traced to a microwave oven in the staff kitchen, open before its cycle finished. The door interrupting the magnetron produced a burst of radio interference that mimicked a real fast radio burst almost perfectly. For 17 years, professional radio astronomers published papers, ran statistical models, and debated the cosmological implications of a kitchen appliance. Every theoretical framework failed for the same reason. Nobody built a model that accounted for hunger. Here's what should unsettle you. If a microwave oven fooled trained astronomers with calibrated instruments for nearly 2 decades, how many other cosmic signals in the archive are sitting there right now, unflagged, misclassified, quietly wrong? Nobody has gone back and checked all of them. One kitchen appliance nearly rewrote radio astronomy. What else hasn't been caught yet? That question about false positives becomes far more disturbing once real signals start repeating. Number 9. The Ferb 1211102 repeater. Laura Spittler, then a postdoc combing through archival data from the Arecibo Observatory, wasn't hunting for anything exotic. She was reprocessing old pulsar survey data, routine work, looking for missed detections buried in the noise. Standard astrophysical models of fast radio bursts predicted single, violent, one-time events, a neutron star collapsing, a magnetar flaring, something catastrophic and final. A burst that happens once should never happen again from the same coordinates. Then, it happened again. And again. Spittler and colleagues confirmed Ferb 1211102 as the first known repeating fast radio burst in a 2016 paper published in Nature. Follow-up work by Shami Chatterjee's team, also in Nature in 2017, localized the source to a dwarf galaxy 3 billion light-years away, sitting inside an extreme magnetic environment unlike anything cataloged before. The failure parade began immediately. A single magnetar flare couldn't explain repetition. A merging neutron star pair couldn't repeat at all, it destroys itself in the collision. A rotating neutron star near a black hole was proposed, then couldn't account for the burst's extreme polarization. Every model that explained the power output failed to explain the repetition. And every model that explained the repetition failed to explain the power. If whatever is powering this thing survives its own explosions repeatedly, at energies our physics says should be self-annihilating, then something out there is stable in a way our equations insist it can't be. What kind of object survives an event that should kill it over and over for years? Before repeating bursts, there was the burst that started it all, dismissed, then vindicated. Number 8. The Lorimer Burst. Duncan Lorimer at West Virginia University was reprocessing archival pulsar survey data from the Parkes telescope, work as routine as astronomy gets, sorting through years-old timing data looking for periodic pulsar signals nobody had flagged the first time through. The standard expectation was simple. Pulsars produce regular repeating pulses. Anything genuinely novel in old archival data was assumed to be instrumental noise, not a new class of astrophysical object. Then his team found a single, isolated, millisecond-long pulse, bright, sharp, and utterly unlike anything cataloged before. Lorimer and collaborators published the discovery in Science in 2007, describing what became the first fast radio burst ever recorded, a signal so energetic it implied an origin far outside our galaxy, compressed into a duration shorter than an eye blink. The failure parade here wasn't about explaining the burst, it was about believing it existed at all. For years, many astronomers assumed it was a terrestrial glitch, an instrumental artifact, anything but real. Skeptics pointed out no one had seen a second one. It took years and multiple independent detections at other observatories before the field accepted fast radio bursts as a genuine astrophysical population, not noise. An entire class of the most energetic events in the observable universe sat unnoticed in archival data for years because nobody thought to look. The universe had already been shouting, we just weren't listening to the right frequency. If one archive hid a discovery for years, what's still sitting in the ones we haven't reprocessed yet? One overlooked archive changed astronomy. One overlooked signal from home became something else entirely. Number 7. The Voyager Interstellar Plasma Hum. Voyager 1's plasma wave instrument was never designed to search for anything exotic. Its engineers built it in the 1970s to measure electron density in the solar wind, a housekeeping instrument, not a discovery machine. The standard model predicted that once Voyager crossed the heliopause, the boundary where the sun's influence ends, the plasma density readings would spike once, sharply, and then go quiet, since interstellar space was assumed to be a near vacuum with little activity to detect. Instead, the instrument kept humming. Continuously, Voyager 1 crossed the heliopause in 2012. And Don Gurnett and colleagues at the University of Iowa reported the findings in a 2013 paper in Science, describing a persistent oscillating plasma wave signal in interstellar space that shouldn't have been there at anywhere near that intensity or duration. Scientists proposed the oscillations came from a single solar eruption disturbing the local interstellar medium. But the humming persisted for months, far longer than any single event should sustain. They proposed instrumental drift, ruled out by cross-checking against Voyager 2 data years later, which showed similar unexplained density structure. The interstellar medium, assumed to be nearly empty and calm, turned out to be active in ways nobody predicted. And no complete model yet explains the sustained oscillation. 48 billion kilometers from where you're sitting, a 40-year-old instrument is recording a sound from the space between stars, and we still don't fully understand what's making it hum. What is the interstellar medium doing that we built no model to expect? That signal came from open space with no destination. The next one had a destination chosen deliberately, and scientists are still waiting to see what comes back. Number 6. The GJ273 Response Signal Search. Douglas Vakoch and the METI International team weren't trying to detect anything. They were trying to send something, a deliberate, structured radio message aimed at a nearby star, designed to be mathematically decodable by any intelligence capable of building a radio receiver. The standard assumption in METI work is that any reply, if it ever comes, would take decades at minimum, dictated simply by the round-trip travel time of light, and that most such projects produce nothing but silence. Forever, in 2017. The snark-calling GJ273b project transmitted a series of messages toward the red dwarf star GJ273, roughly 12 light-years away, chosen specifically because of a potentially habitable planet in its system. The numbers are unforgiving. 12 light-years out, 12 light-years back, minimum 24 years before any reply, if a civilization exists there, if it detected the signal. If it chose to respond, if its response is even recognizable as one. Every explanation for eventual silence is mundane, no one's listening, no one exists, or physics itself makes interstellar reply impractical. But nobody can rule out the alternative. Somewhere in the mid-2030s, radio telescopes on Earth will still be listening toward that patch of sky, waiting on a message we sent before some of you were born. If nothing ever answers, will we ever know the difference between silence and refusal? Not every deliberate signal we send gets tracked for decades. Some unintentional ones from Earth's own past got noticed almost immediately, then vanished before anyone could confirm them. Number 5. SHGB 02+14A. Volunteers running the SETI at-home distributed computing project weren't astronomers. They were ordinary people donating spare processing power from home computers to scan radio telescope data for narrowband signals. The kind no natural astrophysical process is known to produce. The standard protocol required any promising candidate signal to be observed at least twice, ideally from multiple independent detections, before anyone would treat it as significant. A single appearance was assumed to be noise, interference, or error. In 2004, one candidate appeared 3 separate times in the data, all pointing to the same patch of empty sky. Announced publicly in 2004, SHGB 02 and 44A showed a narrowband signal near the hydrogen line frequency, coming from a region between the constellations Pisces and Aries, where no known star sits close enough to explain it conventionally. The failure parade was frustratingly incomplete because follow-up observations at other telescopes found nothing. Proposed explanations included a Doppler drifting artifact from Earth-based interference, a glitch in the software pipeline, or a real but transient astrophysical event too brief to characterize. None was confirmed. The signal simply stopped appearing, and no telescope has recovered it since. A signal appeared from a coordinate with no obvious source, was detected multiple times, and then went silent before anyone could pin down what it was. Permanently unresolved, filed away, unrepeated. Was it noise that happened to repeat 3 times, or a real signal that only spoke 3 sentences before going quiet forever? Silence swallowed that signal. The next one didn't disappear. It got reclassified, then argued about for years. Number 4. The 234 star pulse pattern. Ermanno Bora at Laval University in Quebec wasn't searching for artificial signals. He was testing a mathematical technique for detecting periodic modulations hidden in stellar light spectra, a method originally proposed for finding exotic but entirely natural phenomena. Standard stellar spectra are expected to show smooth, continuous light curves shaped by known physics, temperature. Composition, rotation, structured, evenly spaced periodic spikes are not something ordinary stars are expected to produce. Running the method across thousands of Sloan Digital Sky Survey spectra, Bora's analysis flagged something impossible to ignore. Ermanno Bora and Eric Trottier published their findings in 2016 in the publications of the Astronomical Society of the Pacific, reporting that out of over 2.5 million stellar spectra examined, roughly 234 stars showed a statistically significant periodic pattern consistent, in principle, with an artificial optical signal. The failure parade split the astronomical community. Some argued the pattern was a data processing artifact from the survey instrument itself. Others pointed to interstellar dust or unusual stellar atmospheres as natural explanations. Follow-up observations by other teams failed to reproduce the exact signal in several of the flagged stars. But critically, they didn't rule out all 234. Several remain unexplained by any proposed natural mechanism to this day. 234 points of light in the night sky are still carrying a mathematical signature nobody has definitively explained away, sitting quietly in a public dataset anyone can download. If even one of those 234 turns out to be real, which one is it, and who's watching it tonight? That candidate list stayed academic and abstract. The next one made international headlines within days. Number 3. BLC1, Breakthrough Listen, Candidate 1. Shane Smith, an undergraduate intern working with the Breakthrough Listen project, was doing exactly what interns do, sifting through mountains of radio telescope data, looking for anything that passed the project's automated filters for artificial origin candidates. The standard filtering process is designed to eliminate almost everything. A genuine candidate must be narrowband, must drift in frequency the way a signal from a moving planet would, and must appear only when the telescope points at the target, not when it points elsewhere. In April and May of 2019, a signal appeared that passed every filter. The signal, at approximately 982 MHz, appeared to come from the direction of Proxima Centauri, our nearest stellar neighbor, home to at least one known rocky planet. It showed the narrowband signature and frequency drift consistent with a real, distant transmitter, and it was detected across multiple observing sessions in 2019 at the Parkes telescope before being made public in late 2020. Sophia Sheikh led the technical follow-up, published in Nature Astronomy in 2021. The team found evidence the signal's drift rate matched patterns seen in terrestrial radio interference, and ultimately concluded BLC1 was very likely human-made interference, but very likely is not confirmed. No specific device or source was ever definitively identified as the origin. For several months before that conclusion, this was the single most promising technosignature candidate ever detected by a professional SETI program, and its downgrade to probable interference rests on statistical resemblance, not a smoking gun. If the object responsible for BLC1 was ever conclusively identified, why has no source ever been named? An intern flagged the most promising SETI candidate in history. What JWST is finding now might be even harder to dismiss. Number 2. The unexplained atmospheric anomalies in JWST exoplanet data. Niku Madhusudan's team at the University of Cambridge was analyzing atmospheric spectra from K2-18b, a sub-Neptune-sized planet in its star's habitable zone, hunting for evidence of water vapor and methane, a fairly standard atmospheric characterization survey. Standard planetary chemistry models predicted the detected molecules should follow ordinary photochemical pathways, with no plausible non-biological source at the concentrations found, or should be entirely absent given the planet's expected composition. Instead, the spectrum showed a tentative signature of dimethyl sulfide, on Earth, produced overwhelmingly by marine phytoplankton. Madhusudan and colleagues published their analysis in 2023, reporting possible carbon-bearing molecule detections in K2-18b's atmosphere using JWST data, including a preliminary, statistically uncertain hint of the biosignature gas dimethyl sulfide. The failure parade here is ongoing, not concluded. Multiple independent teams have reanalyzed the same JWST data and reached conflicting statistical significance results. Some support the tentative detection, others argue the signal doesn't clear the confidence threshold at all. No abiotic chemical pathway proposed so far cleanly reproduces the observed spectral features at the reported abundance, and no team has yet confirmed the detection to the standard required for a formal biosignature claim. Right now, in an active peer review argument nobody has resolved, is a real disagreement over whether we've detected the chemical signature of alien life at industrial scale. On a planet 124 light-years away, if the data is real and the interpretation holds, what changes about your species tomorrow morning? Every candidate so far came with a plausible, mundane explanation waiting in the wings. The final entry never got one. Number 1. The WOW. Signal. Jerry Amon was a volunteer astronomer working on Ohio State University's Big Ear radio telescope. Reviewing routine printouts from an ongoing SETI survey, data he expected to be full of background noise, cosmic static, and nothing else. The standard expectation for any single SETI detection was total silence, indefinitely. Big Ear had been scanning the sky for years by that point, and the entire program had returned nothing but noise. On August 15, 1977, the telescope recorded a narrowband radio signal so strong that Amon circled the printout and wrote "Wow." In the margin, a note that gave the event its name. The signal lasted 72 seconds, the exact duration Big Ear's fixed antenna would track a source before Earth's rotation carried it out of view, and matched almost precisely the hydrogen line frequency. 1420 MHz, a frequency SETI researchers had specifically predicted an intelligent civilization might choose, because it's a universal constant any technological species would recognize. The failure parade is the most complete on this list, because scientists have spent nearly 5 decades trying to explain it away and failed every time. A passing comet was proposed in 2017, refuted, because the comets suggested weren't in the right position and don't naturally emit at that frequency. Earth-based interference was proposed, refuted, because the signal's behavior matched a fixed celestial source precisely, not a terrestrial one. A military or classified transmission was proposed. No evidence ever surfaced. The signal was never detected again, not once, despite repeated follow-up searches over the following decades. Somewhere in the direction of the constellation Sagittarius, at some point in the past, something transmitted for exactly as long as our telescope could listen, at exactly the frequency we'd have chosen ourselves, and then it stopped. 49 years later, no natural or artificial explanation has survived scrutiny. What was listening for us to notice? And why has it never spoken again? 12 signals. 12 moments where an instrument built to measure something ordinary caught something it wasn't designed to explain. None of these anomalies live at the fringes of speculative physics. They sit inside real data, from real telescopes, reviewed by real scientists who couldn't make the discrepancy disappear no matter how hard they tried. The universe isn't confused about what it's doing. We are the ones still missing the explanation. One archive, one printout, one spectrum at a time. Every signal on this list ends the same way every unsolved problem in physics ends, not with an answer, but with an instrument, still pointed at the sky, still listening, still recording nothing back. If you want to see more videos like this, click the video on screen now.